Welcome to the Professor's DuBois channel. This is Professor Corey. In this video lecture is a mini lecture based on material from the very end of Chapter 9 starting into Chapter 10. We begin this lecture talking about hybrid orbitals. Hybrid orbitals are required to explain bonding. Looking at the orbital box notation, you can see the valence electrons exist in the 2s and 2p orbitals for the carbon. However, it's not clear how carbon could bond to 4 hydrogens, much less with equal energy. Furthermore, if we were to overlap the p orbitals, we would not get bond angles of 109.5. Hybrid orbitals must form from the s and p orbitals in order to explain these observations. This diagram shows how hybrid orbitals can be formed of equal energy. The shape of the hybrid orbital is such that it can place the bonding electrons at 109.5 degrees apart in a tetrahedral arrangement. In our previous example, the hybridization was what we call sp3. This was due to the number of orbitals needed, which equals the number of domains. We had 4 domains, so a total of 4 hybrid orbitals are required. The chart above shows how we can use the number of domains to determine the hybridization present. Double bonds consist of both a sigma and a pi bond. Note that sigma bonds are formed from orbitals whose lobes point toward each other, but pi bonds result from parallel orbitals. A double bond always consists of one sigma bond, where the electron pair is located directly between the atoms, and one pi bond, where the shared pair occupies the space above and below the sigma bond. Carbon is sp hybridized, leaving 2 p orbitals. Oxygen is sp3 hybridized, leaving 1 unhybridized p orbital. The pi bonds result from overlap of these p orbitals. Each nitrogen atom in the nitrogen molecule has 2 sp hybrid orbitals and 2 unchanged p orbitals. The sp hybridized orbitals are used to form the sigma bonds between the nitrogen atoms and to hold the lone pairs. The p orbitals are used to form the pi bonds. Each pair of overlapping p orbitals holds 1 electron pair. Chapter 10 covers gases. We're familiar with gases from our previous lectures, but this chapter dives deeper into the properties of this state of matter. Gas pressure is a common measurement in the laboratory and even at home. We should regularly check our tire pressure in our automobile to reduce premature tire wear. In chemistry, it's common to have to convert pressure units. There are many different pressure units. I think my favorite might be torr. The unit torr was named after Evangelista Torricelli, an Italian physicist who discovered the principle of the barometer in 1644. I wonder what normal people did in 1644. In addition to pressure, the other important variables when working with gases are volume, temperature, and amount. There is a relationship between pressure, temperature, and volume for gases that can be seen using this diagram. The relationship does not exist for solids or liquids, only gases. If I were to hold temperature constant by physically holding the paper under the letter T, and I increase the P side, the V side of this paper would go down. Likewise, I could say at constant temperature, an increase in pressure will decrease the volume of a given amount of gas. We can call this an inverse relationship. Other relationships exist. At constant pressure, increasing temperature will increase the volume of a gas. There are more, and they can all be visualized using the PTV card. Boyle's law relates pressure and volume of a gas. Volume is proportional to 1 over pressure. The product of pressure and volume is constant when temperature and amount are held constant. Therefore, it's possible to calculate a new pressure or volume of gas sample when one of the properties is changed. Charles' law examines the relationship between temperature and volume of a gas at constant pressure. When the pressure and amount of gas are held constant, decreasing the temperature of a gas sample decreases the volume of the gas. Because the ratio of gas volume and temperature is a constant, it's possible to calculate the new volume or temperature of a gas sample when one of the properties is changed. Avogadro's back, and he's back to tell you the relationship between volume and the number of particles of gas at a constant temperature and pressure. We end this lecture with a sample problem. Notice how the data is pulled from the question and listed. It's easy to see from the data that we're looking for the relationship between pressure and volume. This is Boyle's law. Using the PTV card, we can predict a decrease in our initial volume with the increase of pressure. Our answer looks reasonable and is reported to 3 sig figs. Thanks for watching. Please give the video a thumbs up and subscribe if you'd like to see more mini lectures on the Professor's DuBois channel.